Good morning, ladies and gentlemen. So we are at the top of the hour. It's 8 o'clock, and we'll be starting our session on quantitative data analysis. So I want to welcome you all to this session, the 2026 edition of the Manuscript Writing Hub training on quantitative data analysis. So essentially, what this course tries to do is to equip us with some knowledge, foundational knowledge on quantitative data analysis that will be helpful for our careers as professionals and as researchers. So just a quick lowdown on some of the things we expect. Most of the information you're going to be having, you'll get them on the WhatsApp platform, which will be our source of communication between participants. So for the sessions, it's going to be a 2-hour session. Our trainers are here. Our trainer will give a lecture, after which you are free to put down your questions on the chat box, and we'll do as much as possible to answer all the questions. But any questions that will not be, maybe for want of time, may not be answered here, we'll continue them on the WhatsApp platform. Again, we want to just appeal to all participants to ensure your devices are well named so that we don't have any, we are able to keep track of everyone's attendance records. I see on the platform, I see someone is HP. If you have things like that, HP user, please just try to rename it into your own name so that we can keep track of our participants. All right, so there's a lot to do today, so we don't want to spend too much time on other things. You get as much information as you need on the WhatsApp group. So we'll just move on to our training for today. Our lead trainer for today is going to be our trainer over the course of the 4 weeks sessions is Dr. Olaniyi Taiwo. And Dr. Olaniyi Taiwo is a seasoned public health expert and is a clinical researcher with extensive experience in oral health, research methodology, epidemiology, and biostatistics and ethics. And he has led numerous national and international initiatives aimed at advancing oral health equity, strengthening research capacity, and shaping evidence-informed policy. Currently, he serves as the director and CEO of the Inter-Country Center for Oral Health for Africa. It's my pleasure to welcome, to take us on today's session, Dr. Olaniyi Taiwo. You're welcome, sir.
Thank you so much, Dr. Sahon. Thank you, everybody, for having me. It's a pleasure to have an opportunity to share some of these insights in quantitative data analysis. And like Sahon said, there's really a lot for us to do. I will just set the ball rolling by me sharing my slides, and then starting with some preamble, and we continue from there on. Just 1 minute. All right, my name is Niyi Taiwo, and I'm a research methodologist. I like introducing myself like that because that's an area of passion for me. I'm so optimistic that by the time we are done today, we would have an idea about some of the concepts in quantitative data analysis, and we will be able to also look at descriptive statistics. By the way, am I audible before I just continue? Osam?
Yes, sir, you're audible. We can hear you loud and clear.
Beautiful. All right, so we'll just move on. I hope to be able to finish in a reasonable time so that we'll have time for comments, questions, contributions, and just to interact together. I just want to let us know that not everything here is my own idea. There are some of the proper materials I sourced online, and they are for educational purposes. I'm not claiming ownership of everything here. You know, those who owns it, there's due respect for their work. Great. So for the class, the first question I would like to ask, I'm not expecting your response anyway, is just to let you know why you should care about statistics. When you have bad data, definitely you have bad decisions. And us in the medical line, The life of our patient depends on evidence, and evidence is a function of statistics. It's a function of data. And even in the government, I work with the government, we make policies every now and then. It's still a function of statistics and data. If there's no statistics or data, we'll have to start guessing, and that will not augur well for the populace. For this class of this morning, I've been told we are looking at 4 different topics for spanning over the 4 weeks in February. Today's own is just an introduction to quantitative analysis and then descriptive statistics. I think by next week, we'll be looking at correlation and chi-square. The week after that, t-test and ANOVA. And then hopefully by the last week, that will be a regression and contingency table analysis. These are topics that actually take so much time, even per one, but we are just trying to make it in a form that at least this 1 month, we'll be able to grasp something so that you'll be competent enough to understand this analysis and maybe be able to do them on your own. I want us to just look at this concept. These are the concepts that will form the foundation of our class. To know what research is, that's very important. The research process, what is variable, what are measurement scales? These 2 terms, everywhere I talk about quantitative analysis, those are the cardinal foundation for anything data analysis. If you don't know what a variable is and the types of variable, and you don't know the measurement scale for the variables, then you can't actually analyze. You'll be confused and you'll mislead. You'll go into error. So they are very cardinal, and I'm going to briefly look at them in the course of our discussion. So I have a definition here for research, and it says that it's a systematic investigation that includes development, testing, and evaluation designed to discover and contribute to a body of knowledge. This definition is cardinal. This is not a class for us to talk about research methodology, but I want you to know that all the words chosen there are cardinal, that research is systematic. It's not haphazard, and it follows a design. And the whole essence is to discover, to bring out new information such that we can contribute to a body of knowledge. For example, when we study why maternal mortality is higher in northern Nigeria than southern Nigeria, that is research. We are trying to bring out, the reason. That's why I put this in red. You want to bring out the reason so that we can add that to the body of knowledge, and by virtue of that understanding, we can bring up policies that can help address that issue. This is a research process I designed and I've been using everywhere I talk about research. Our research starts from the research title or the research problem or the research question you have, where you now go over and check the literature to see if it's been done before or it is novel. And then if it's quantitative, you bring up an hypothesis of what you think you are going to study. You look at the different approaches and the design you are going to use to study your question. If it's quantitative, you calculate your sample size, and once you have a sample size, you determine how you are going to select the samples, the variables and measurements you are going to be doing. That is for your data collection, which is the next step, and then the data analysis before you report your findings. This is what we are talking about. So you can see that we have actually assumed that we have gone through all these stages in this process to be talking about data analysis. So don't forget that. Variables, like I said, they are the building blocks for this class. What's a variable? A variable is anything that can change or vary. Anything that can change or vary, ranging from simple concepts like your age. Your age yesterday is not your age today. You've added a day. So your age has changed. Your height changes, although it gets to a particular level where it might remain like that when you're old. And even when you get older, it tends to reduces. I'm sure you have seen some of our parents and grandparents. They become smaller in our faces, and then it can be complex things like the satisfaction level, socioeconomic status, maybe health status, whatever. There are many things. Anything that can change is a variable, and we need to know that we live in variable, we work with variable, and as scientists, we are always collecting variable. Example of variables are age. Your blood pressure is not constant, it fluctuates. Your gender, somebody is born either a male or a female. Now we have all manners of gender in the world. I don't know where somebody even now belongs. Your income also varies. What you earn yesterday might not be the same today. Even for those who earn salary, occasionally there are some allowances that changes the value. The temperature changes. If you are here in Jos, where I am, and then I take the temperature, and I ask you to take the temperature wherever you might be in other parts of Nigeria, you will see that there's a variation. So anything that can change is called a variable. And this is different from a constant. A constant does not change, but remains the same. Let me give you an example. This is a rectangle. Let's assume that is our length and breadth. The area of the rectangle is length times breadth. If I take this rectangle to Lagos and I want to take the area of that rectangle, it's still length times breadth. I take it to Port Harcourt, I take it to Kano, I take it to Sokoto. So that's an example of a constant. The area of a rectangle is the same area everywhere. Even if I go to the moon and I want the area of a rectangle, is the same formula. So there are some things that have fixed values. We call them constant. We call them constant. The value of pi, 3.14. All of us from secondary school days, we know that is a constant. Anywhere you go, pi is pi. So we have variables, things that can change, constant that has a fixed values. Okay, the speed of light is a constant. The formula of an area of a triangle, the formula of a volume, all those ones are constant. Now, let's look at the types of variables. Variables can be classified into two broad categories. Please just follow me carefully, because if you have this grasp, it's easier to talk about data analysis in whatever form. There is a quantitative or numerical variable, and we have qualitative or categorical variable. Quantitative, you can quantify. That's why it's numerical. The qualitative, you can classify it or you can categorize it. That's why it's called categorical variable. The quantitative variable is the one that you can measure numerically or you can count. You can measure your weight, your height, or you can count the number of people in a household. You can measure your pressure. You can measure the force. You can measure anything you can measure that can be ascribed with a number, or whatever you can count is quantitative. So quantitative variables can either be continuous. This one is the one that you measure, or discrete. This is the one you count. Continuous means that anything that can have a decimal point, that can assume an infinite value, is continuous. So, like your weight, if you go to where you have a digital weighing scale, you can have maybe 80.3, 80.21, whatever. As long as you can have a decimal point behind that measurement, it is called a continuous quantitative variable. Like length, like distance, or anything that can have a decimal point. Unlike the discrete one, the discrete is whole number, something that must be whole. It cannot have a fraction. Like the number of people on this program now, we cannot have 50.1. 0.1 does not exist for a human being. So that one is not a discrete. Discrete is whole number. A variable is considered continuous if it can assume an infinite number of real values, like I said earlier, on distance, weight, height, temperature, pressure, force, all manners. So in general, all measurements are continuous variables. All measurements. Whenever you are doing a study and you're collecting data and you say measurements, they are continuous variable. They are also known as interval variable. As opposed to the continuous variable, like I said, a discrete variable can only take a finite number of real values. They can be counted. You have the whole numbers in a discrete variable. For example, the number of eggs laid by a hen. If you have ever had like small chicken or a poultry, the hens are always whole. They cannot have half egg or whatever. I mean, the eggs are whole. The number of children in the family, number of patients in the clinic, number of people in this presentation, anything that is a whole number that can be counted, not measured, counted, they are called discrete quantitative variables. On the other side, like I told us, we have two types of variable. We also have qualitative variables. Those are the ones that I said can be classified or categorized. They are not, cannot measure them numerically, and here the responses can be put in a specific category. And these categories must either be mutually exclusive or exhaustive. I'm going to explain this in the next slide, and I'm going to use this example. So let's talk about educational status as an example. If you have a questionnaire and you are trying to get the educational status of your respondent or participant, it's either they never went to school, which I can call like 0, or possibly, okay, let me just say no school, and then maybe they had a primary education or secondary school, that is here, or tertiary. Tertiary here means anything above secondary school. So we have 4 classes, and as it is, you can only be in one of the group. Look at mutually exclusive here. It says each possible survey response should belong to only one category. You cannot be a primary school graduate and claim secondary school. No. It is either you are primary, or you are secondary, or you are tertiary, or you never went to school. The variables must be exhaustive. That requires that the categories should cover the entire set of possibilities. So, I mean, in educational level, it's just one of those 4. There's nothing else. No matter how it is, you must fall into one of these 4 levels. And when we say tertiary, anything above secondary school, even from poly down to postdoctorate, is just tertiary. So that's how it's classified. The same thing can be used for maybe marital status. It's either you are single, you are married, you are divorced, you are widowed, you are separated, you are cohabiting. I think it's about 6 or 7, but you can't be 2 at the same time. You just have to be somewhere. Maybe your occupation is either you are working or you are not working. You cannot be saying that you are not working and then you are seeking. You just have to fall in a particular category. So for the qualitative also, it can either be ordinal, ordered, or nominal, unordered. When we say ordinal, it denotes ranking. So it can either be like an ascending order or a descending order. So qualitative can be ordinal, where your variables can be arranged either in an ascending order or descending order, or nominal, where it's just a label, where you don't have any particular natural order of the variable. For example, for the ordinal, the position in a race, first, second, third, they are all categories, but it is arranged in hierarchy in the sense that somebody came first, followed by the other person. Socioeconomic status, we always ask that question in our questionnaire. You can have low income, middle income, high income, and you can even give monetary values to them. So note that the hierarchy does not express the degree of magnitude, because let me give an example. Maybe in an exam, somebody scored 90%, the other person scored 70, and then the third person scored 69. This is first, this is second, this is third. But you notice that the magnitude in between them differs. So it's not really a reflection of the magnitude in between, rather it's just to denote that one is higher than the other. And there are some natural ordering also that are ordinal variables, like stage of pregnancy. You hear of first trimester, second trimester, third trimester. Cancer stages, we have about 4 of them. HIV stages, about 4 of them. Many of us we use Likert scale, where we have maybe like strongly disagree, neutral, agree, strongly agree. It's also an ascending or descending order, depending on how you want to position it. So all these are ordinal variables, and you need to know the kind of variables you have in the course of looking for how to analyze your data. Nominal variable, like I said, is just a label. It doesn't have a particular category. It's just a label for that particular variable. Your like sex, male is a label, female is a label. Religion, Islam, Christianity, traditional, Hinduism, there are so many, they are all labeled. It's not as if one is higher than the other or one is less than the other. Occupation can be a label, and occupation can also be rearranged to be an ordinal variable depending on the kind of data you are collecting. The color of your clothes, blue, red, green, yellow, it's a label. Color does not have hierarchy. Okay. So contrary to ordinal variables, there is no natural ordering for nominal variables. So this is just a summary of variables. They can be quantitative or numerical. They can be qualitative or categorical. The quantitative, I said, can be measured or counted. This is for measurement. This is for counting. This is the one that is just a label. This is the one that has an order. Remember that ordinal variables are also called rank variables. So don't get confused about that. Now, let's quickly talk about measurement scales. These are part of the building blocks for data analysis. When we say measurement scale, it just means the assignment of numbers to a variable. The assignment of numbers to a variable. If you collect data, which we are going to explain later on, in a questionnaire, and you are trying to enter it into a spreadsheet, either Excel, SPSS, data, or any spreadsheet you're using, you will realize that you normally use numbers, for your variables. Maybe somebody, are you happy? Yes or no. And you say yes is 1, no is 2. Or you can say yes is 2, no is 4. It's just giving numbers to a variable. So in statistics, the kind of descriptive statistics and inferential statistics that you do will depend on the measurement scale of the variables that you have collected. And there are 4 types of measurement scale. We have the nominal scale, ordinal scale, interval scale, and ratio scale. If you note, these 2 are the qualitative variables, while these 2 are the quantitative variables. Nominal scale and ordinal scale, it follows the nominal and ordinal variable. Interval scale and ratio scale, this is the one that actually follows the quantitative scale. I will explain the interval variable as we continue. The type of measurement that we do, for the nominal scale, if you put a number, that number that you put is just to identify the variable, it's just a label. I gave an example earlier on that maybe you have a question where you say yes is 1, no is 0. You can as well say yes is 3 and no is 11. These numbers don't mean anything apart from just being a label. So you cannot find the mean of yes, you cannot find the mean of no, because it's just a label, it's just a category. You get the point. So that measurement scale is cardinal for you to be able to know the particular type of analysis. So when we go to the ordinal scale, the numbers that you put, they are rank ordered. Okay, we talk of a cancer stage, and I said there's stage 1, stage 2, stage 3, stage 4. If you put a stage 4, it shows that it's debilitating or something that's about to cause mortality. Stage 1 means maybe the early stage 2 and stage 3 are in between. However, despite the fact that the number shows the rank order, you cannot find the mean of this number because it's just an order. It doesn't give it that value for it to be able to undergo mathematical, calculations, although there are some things that can be done with them. Interval scale, here, the numbers, they have a label. They also have like an ordinal level, but they don't have a 0 value. The 0 value is arbitrary. And what do I mean by that? Let me give an example. When I say 0 degrees centigrade, 0 degrees centigrade does not mean there's no temperature. It means freezing. So 0 in temperature has a meaning. And that is why it's interval, because so any place where you can have measurements that can have like a positive side and a negative side, it's an interval scale, like a pH. When you have a pH value, it can be interval. So when something is negative, it's very acidic. When it's positive, it's a bit alkaline. The same with temperature. When it is positive, it's getting more and more hotter. But the lower it goes beyond 0, it becomes more and more colder. So the 0 value is not arbitrary. The 0 value means something, and that is the interval scale. However, for the ratio scale, the 0 is not arbitrary. And all measurement and counts, that's the quantitative variable, are actually based on ratio scale. So if I said that the distance covered is 0, that means no distance is covered. That means 0 has a value. It means 0. That is the difference between ratio scale and interval scale. Most of your data will be collected in ratio scale, ordinal, and nominal scale. Most of your data. So those are the 3 scales, measurement scales that matter to us. Look at this example. For a nominal scale, somebody can be hypertensive or not hypertensive. It's just a label. It's just a label. It's either you are hypertensive or you are not. For the ordinal scale, possibly your hypertension can be stage 1, stage 2, stage 3. If you are using hypertension for an example, or if you are using pregnancy, it can be stage 1, stage 2, stage 3. For the interval scale, I used the example of temperature earlier on. 0 does not mean there's no temperature. It just means freezing. And you can have minus, in temperature. Like I heard about Canada of late. I saw one news that is going to like minus 50. And that's very cold, very, very cold. So that's an interval scale. Ratio is whatever can be counted or measured, like your temperature, like your BP, like your weight, like your height, like distance. All those can be measured or counted. Okay, so in the hierarchy of all this measurement scale, the ratio scale is the strongest, where you have an absolute zero. As you can see, it's higher, is the one that is highest among all the measurement scale, while the weakest is nominal scale. Like I told you, nominal scale is just a label. You cannot add, you cannot divide, you cannot multiply, but anything mathematical can be done with a ratio scale. You can add, you can divide, you can subtract, you can multiply. So you must know the kind of measurement scale to help you in your data analysis. Let's talk about data. Data now is a collection of observations or measurements that you use to analyze or make decisions. They can be numerical, they can be count, they can be categorical, they can be labels or classification. This is very important. Please let me go over it again. Data can be numerical, it can be counted or measurement, they can be categorical or they can be classifications. Therefore, data is a set of values of qualitative or quantitative variables. So in short, data is a collection of variables. So one variable can be age. So if I take the age of one person, the age of another person, the age of another person, and maybe like 5 or 6 people, then I have data. If I can take the weight of 1 or 2 or 3 people, then I have data. So data is the starting point for analysis, and it's examined, manipulated, and interpreted to draw conclusions or make predictions. Okay, so these are the types of data. Invariably, the types of data, we just follow the type of variables. So data can be quantitative, where we have continuous data and discrete data. Or data can be qualitative, where you have nominal data or ordinal data. So since data is a compilation of variables, the type of data will just follow the type of variables. Look at this example. On this side, I have data, which is the weight of about 6 people. 25, 33, 32, 28, 26, 22 kilograms. That's data. Here I have what we call information. And look at what it says. 4 individuals are in the 25 to 30 kilogram group. 2 individuals are in the 30 to 35 kilogram group. That is just information. But on the right side, I have statistics, because there I can now have the mean of that data. I can have the median of that data, and I can have the standard deviation of that data. So that is the difference between data, information, and statistics. So if you weigh like 25 kilograms, that is data. When I say 4 children are underweight, that is information. When I calculate the mean of the weight, okay, so if I have to correct that, if like say 5 of you weigh 25 kilograms, because I said earlier on that data is a compilation of variables. So if 5 of you weigh like 25 kilograms, that is data. But if I say 4 children are underweight, that is information. And when I calculate the mean of the weight of 4 people, that gives me like statistics. So data are raw facts or figures. Information is data that has been processed so that it's more meaningful, while statistics is the science of data collection and analysis. I repeat again, statistics is the science of data collection and analysis. So it refers to information obtained by mathematical operations on numeric data. That means that we can have data that is not numeric, and that's qualitative data. We'll talk about that as we continue. So data analysis is the process of transforming crude data into information or statistics, where you can now make decisions, where you can have evidence, or you can then have policy. And there are 2 approaches to quantitative data analysis, which is the course we are having for this month. It can be descriptive analysis or inferential analysis. When we say descriptive, it's more like what is happening here, what are we seeing here on ground. And when we say inferential, it's like we are trying to infer based on what we have done to a population. So what is happening here? What does it mean for Nigeria? So you have done a study somewhere, possibly like say maybe Edo State, to look at the views of people to the present political situation. And after you have done your study, you are now trying to infer what that means to Nigeria as a whole. That is inferential. So descriptive statistics refers to information that summarizes or organizes the basic features of an entire set. While inferential, at the level of inferential statistics, the information extracted from the data is now used to draw conclusions, to make inferences, to make predictions to a larger population. So it aims to generalize findings to a broader context. That is the essence of inferential statistics. What we are talking about today is just descriptive statistics. And when we are doing analysis, it is either you are working on one variable, where we call it a univariate analysis, or it might be more than one, two, or it might be more than two, multivariate. When it is two, it's called bivariate. And this two is actually where inferential statistics come in. But this is where descriptive statistics come in, because in descriptive statistics, you are picking one variable, either age, gender, maybe height, distance, income. You are just picking one variable and you are describing it. So whenever we have more than one variable, most of what you do is inferential. So let's now look into what we have for descriptive statistics. We've said that it refers to a method used to summarize and describe the main features of a data set. So when you have a data set, remember you have many variables in a data set, starting from gender, marital status, age, religion, and whatever variables we have collected in your data. And some of what is used to describe that is the measures of central tendency and central variation. They provide an overview of the data and help identify patterns and relationships. So descriptive statistics help you to explain to other people what is happening in your data. Before we begin to describe data, we need to decide what sort of data we have. Remember, I said this is cardinal in our descriptive statistics and even inferential. Remember that data can be quantitative or qualitative. In the quantitative, data can be continuous data or discrete. Under the qualitative, data can be nominal or ordinal. By now, I believe you understand what those mean. So for the univariate analysis, which I said is descriptive statistics, it can be categorized into two: when your variable is continuous or your data is continuous, or when it is categorical. Now you can see the difference. If you have a continuous variable, we can do what we call a measure of central tendency. You can find the mean, the median, and the mode. Why? Because a continuous variable is measured in a ratio scale. And I said ratio scale can be added, divided, subtracted, or multiplied. Likewise, we can also do a measure of variation. And that is where we have variance, standard deviation, the range, the percentiles, interquartile range. And we can plot the distribution curve. That's like the normal curve for that data. And we can also do some charts and graphs like histogram, box plot, stem plot, dot plot, line chart, time series plot. All these are very good for a continuous variable. So you are the one that will be able to decide which particular kind of analysis you will do, descriptive analysis you will do for your variable, for your data, if you know the type of variable it is. I said for the continuous variable, these are what you do. Now, if your variable is categorical, that is, it's either nominal or ordinal, these are what you can do. You can do a bar chart, a pie graph, a Pareto graph, we'll talk about that. You can do a count and frequencies and percentages. All these three are what we normally put in a table. We put them in a table just to summarize what we are doing. Let's continue. So descriptive statistics can be two. Either you organize your data or you summarize your data. Those are the essence of descriptive statistics. You can organize them into tables or graphs, or you can summarize them by the measures of central tendency, mean, median, and mode, or by variation. So that is descriptive statistics. It's either you organize the data or you summarize it. And if you're organizing it, like I said, it can be under tables or graphs. And when you are summarizing, it can be under the measures of central tendency, mean, median, mode, or variation, where you have the variance, standard deviation, the range, interquartile range, percentiles, all like that. That's for the summarizing of data. And this one works with continuous variable. This one works with qualitative variable. That is either it is nominal or it is ordinal. So we are looking at the organizing of data. And I said we have tables and graphs. And look at here, please. For you to organize your, your data, your data needs to be ordinal or categorical. Now, you can see here, it says continuous data. Yes, occasionally we can use tables to organize continuous data. That is when we group the data. Sometimes, you have this group interval between 0 and 10, and then you say 11 to 20, then 21 to 30. Now, this next while were continuous variables, but you have grouped them And by grouping them, you have made them to be categorical. So that is when you can now use them on that table. And then we talk about graphs. Let's just continue. So for the tables, we use a frequency distribution in a table. It displays the frequency, or the count, and it helps to organize the distribution. The objective is to provide insight, about the data that cannot be quickly obtained by looking at the original data, because the data is going to be massive and very large. Looking at them, you cannot make sense out of it, but you can organize them in a table to give you a brief insight of what you have. Look at this. Okay, let me just say 1, 2, 3, 4, 5. So look at table 1. Number of toys cars sold, per month. In January, the 20 was sold. Looking at that table, you can see that in the month of May, that was when the highest number of toys was sold. It's been organized in a very simple way for you to quickly know when you have the highest frequency. Look at table 2. We have satisfaction. How many people? Very satisfied, there were 59, and very dissatisfied, there were 5. It has organized the responses. These ones are qualitative variables. This one is an example of ordinal. If you look at it, it's a Likert scale. Look at table 3. We have the number, we have the frequency, and we have the cumulative frequency. I'll talk about that as we continue. You can also use tally. Look at table 4. You can use tally where you have those four lines, and when it becomes 5, you strike through, and then you have your frequency. So all these are just tables for your frequency distribution for your data. Now look at, let me put this one, 1, 2, 3. Look at table 1. It's supposed to be for a group frequency when you have like an ordinal, a continuous variable. But there's a reason why I'm putting table 1. See the class interval, 15 to 25. This is wrong, this is wrong, this is wrong. This should not be 25 to 35 again. It should be 26 to 35, because if you have a number that is 25, where do you put it? Is it here or here? So you should be very careful when making your group interval that it doesn't overlap, because, and the same thing here, 35 is overlapping here, 45 is overlapping here. So your group interval must be mutually exclusive. Remember, we mentioned it in our qualitative variable. It must be exclusive. There should be no overlap. And then here we have category and the frequency. This is an example of a continuous variable that has been put in class interval. And we also have an example here using tally and then the frequency eventually. Now, cumulative frequency table, that's the term I'm just bringing in. Look at this table here. We have the frequencies here. And then as it goes down, we are having the cumulative frequency. For the person that read only 2 books, it has 1 frequency, and that is 1. For those that have read 3 books, for them to have read 3 books, they must have read 2 anyway. So that means that cumulatively, under 3, we have 3, that is 1 plus 3, giving 4. And on like that. 4 plus 5 gives 9, 9 plus 2 gives 11, 11 plus 1 gives 12. That is cumulative. As you are going down, you are adding the frequency of the next group on like that. It can also be done for a continuous variable that has been put in class interval, and you have cumulative frequency. 2 plus 4 gives 6, 6 plus 2 gives 8, 8 plus 1 gives 9, and that's how we get that. Relative frequency. What we mean by relative frequency is, okay, we have our variable here, and this is the frequency. How do we get the relative frequency? You get the total of the frequency. 2 plus 2 plus 4 plus 2 plus 4 plus 2. That is 16. So to find the relative frequency is to put the frequency of maybe group 1 or grade 1 over 16. And you have 0.125. 2 over 16, the same thing there. 4 over 16, the same thing there. And you can turn them to percentages. The good thing is that when you add the percentage here, it should amount to 100%. So that is how we have relative frequency. It's clearer in this table. We have the total here. We have 4 over 20. It gives us 20% or 0.2. 5 over 20 gives us 0.25 or 25%, on and on. And like I said, if you add everything, you should get, excuse me, 100. That's relative frequency. Now let's talk about graphs. We're still talking about organizing data. Number 1 is histogram, and it's used to display frequency distribution of interval and ratio level data. Are you seeing why we need to know variables? Interval and ratio level data. It's like a bar graph, but there's no space in between them. It cannot be used to display information of more than 1 variable. and you position them on your X and Y axis, and you have your rectangle that is drawn above each class interval, with its height corresponding to the interval's frequency, relative frequency, or percent frequency. Let me show you an example. This is an example of width, and you can see that we have bars, stacked together. And the interesting thing is that there is no space, between the bars. They are like next to each other. This is to reflect the fact that the class interval, is continuous. Is continuous. There's no space in between. So that's an example of a histogram. These are things I'm sure we are aware of. This is another example of a histogram, the weight of students, and you can see them next to each other. We also have another histogram here, but in this histogram, there's something I'm trying to show, and that's the fact that it's symmetric. And what is that? You can see the way it goes. It's more like even on the left and even on the right. This one is symmetric. And here we have what we call a skew. A skew, when one side is longer than the other. This one has a longer left, compared to the right. So it's moderately skewed to the left. Here we have a skew to the right. It has a longer right part when you can construct a histogram. And then here we have a very long skew, to the right part when you construct your histogram. And there are many kind of observations or data that can generate this kind of appearance. Skewness is a measure of asymmetry, okay? Because normally a normal distribution should be symmetrical. We call it a bell shape. But if one side is longer than the other, it is asymmetric. So it's a measure of asymmetry. Positive skewness is a long tail. Negative skewness is a long left tail, like we saw in the previous histogram. So these are different shapes of histogram. This one is symmetric. This one is skewed to the right. This one is skewed to the left. Okay. We'll talk about this now in the next slide. So that's different types of histogram. Kurtosis is a measure of the extent to which observations cluster around a central point. Kurtosis. So for a normal distribution, the value is supposed to be 0, but there's something we call a leptokurtic data, where it is more peaked. So this is a normal distribution, for example. You can have a distribution that is like this. You can see that it's different from this. Or you can have a distribution that is like this. You can see that it's also different from this. This is the leptokurtic. They are peaked to the center, and platykurtic is flatter. It's flatter. Instead of it to be peaked, it's flatter. So this is an example here of a leptokurtic, distribution or histogram. This is the platykurtic. You can see that it's flatter, unlike this one that is peaked. And in case you come across terminologies like that, it's just for you to understand, what it is trying to say. That's a picture of a normal distribution. Like I said, it's bell-shaped, like half on the side, it's the same with the half on the other side. Frequency polygon is something you'll come across again. It's a graphical device for understanding the shapes of distribution also. They serve the same purpose as histogram, but especially helpful for comparing data sets. The polygons are also a good choice for displaying the cumulative frequency of data sets. Let's see what I'm talking about. So this blue here is a histogram. So the frequency polygon is just a line that is joining the middle part of the top of the bars, as I'm just marking here. So that is just a line that is joining the middle part. That line is the frequency polygon. Look at this part here. It's clearer here. It goes through B, it goes through C, D, and E. What we have here is a histogram, but that red line that is joining them is the frequency polygon. And that line makes you to see, if it is symmetrical or there's a kind of skew or there's a kind of kurtosis on one side or the other. This is another example of a frequency polygon. It's just that line that joins the middle part of the tip of the histogram. So let's assume that the bars, the rectangular bars are removed. You just have a straight line like that, to give you an impression of what the distribution was looking like. So this is an example of a frequency polygon showing the scores of a test and the frequency, and we have that there. This is another example of a frequency polygon. And these are two frequency polygons like superimposed on each other to compare two data sets, okay? A bar chart is used to display nominal and ordinal data. Are you seeing the difference with histogram now? So a bar chart is for qualitative variables or qualitative data. A single bar chart can present more than two variables or data, okay? And in a bar chart, they have spaces between them, and these spaces are there to emphasize that they are different categories, they are different classes, okay? And the height is proportional to the frequency. This is an example of a bar chart. I'm sure all these are just like revisions for you, so I will just be a bit faster in this area. These are a bar chart. You can have the blue one talks about the British home students, the red one talks about the international students, for in UK, just to try and compare the numbers. This is for men, this is for women. And from here, you can see that, let me just take the example of women. For the women, the international students are less in proportion compared to the home students for the 3 different years under consideration, 2010 to 2012. So that's the bar chart. This is another bar chart here. This one is one particular variable. This is another one. This is another variable, this is another one. So you can use it to check for more than 1 or 2 variables. Look at the favorite color here. It's a bar chart because color is a label, a nominal variable. You have red, blue, green, yellow, and pink, and all of them are distinct. From this particular bar chart, it's obvious that yellow has the highest frequency and green has the lowest frequency. As simple as that. This is another example of a bar chart having the label on the vertical axis. Now, this is an example of a Pareto diagram. I said we are going to explain it. A Pareto diagram is just a combination of 2 kinds of charts. We have the bar chart A, B, C, D, E, F. This line here is the cumulative frequency. Remember the cumulative frequency. You add the first one with the second one, with the third one, with the fourth one, down to the last one. So you can see that as the variable is continuing here, the frequency is also increasing, and I told you it should be 100% when you have it in percentages. So it's just a combination of a cumulative frequency curve and a bar chart. That is what we call a Pareto diagram. And that's all, a cumulative frequency and a combination with a bar chart. A pie chart is something similar to a bar chart. It's also used for nominal and ordinal data sets. The segments can be shaded differently or patterned differently to differentiate among them. It's normally done like in a circle, where by frequency, you try to find the proportion, over 360 degrees of where a particular variable would occupy. That's just a pie chart. Okay, so it's something like this. You have done a calculation. It's something that the software can do for you, or you can do it for yourself. And looking at this pie chart of countries, without wasting much time, it's obvious that Germany has the highest proportion, and the least is Australia, where they have different coloration to differentiate them, one from the other. A pie chart can also be used like in comparing 2 different dispensations. This is 1998, this is 2007. And the heading there says population of countries of the EU in 1998 and 2007 by percentage. In 1998, for example, Italy, which is green, it was 11.8, and in 2007, 11.9, an increase of 0.1%. And you can compare for the different other countries in the chart. It can also be done like in a donut like this. It's still the same thing, it's just that it's another design. And just for an example, talking about the bar chart and maybe qualitative data, customers visiting a fast food were asked to rate the quality of their experience as either being excellent, above average, average, below average, or poor. If you look at these responses, it's a kind of variable, and that is an ordinal variable because it starts from excellent and it goes down to being poor. And then so that is the variable. And this is the finding from 20 customers, and this one is the data set. Okay, so you are getting it now. We have different responses from 20 customers as the data set. And looking at it like this, it might be difficult to make head or meaning out of it. So that is the rating from 20 customers. We can turn it to a table. For poor, we have 2 people saying poor. For below average, there are 3. For average, there are 5. Above average, there are 9. Excellent is 1. And we have it in a table form. We can also get the relative frequency, which I said earlier on, is just by putting 2 divided by 20 for the first line, 3 divided by 20 for the second line, and on like that. And we have it out like that. And you can find the percentages. And like I said, if you add it, it should give you 100. And then we can have a bar chart. Because it is a qualitative variable, you'll need to have them separately without any form of space, with space in between them. And from the bar chart, even without much ado, we can see that above average has the highest frequency. Likewise, here also, above average has the highest frequency. And even we can also make it into a pie chart, because a pie chart and a bar chart work on the same type of variables, nominal and ordinal. And you can see here also that above average, is taking a large pie out of the pie chart. Another way to organize our data is stem and leaf. And here we have, it's another method, although not in that table that I gave earlier on. We have a series of numbers where we identify part of it as a stem, that is putting it by one side, and then the latter part as the leaf. This is where that stem and leaf came from. It's like a tree trunk with the leaf by the edge. We have a series of numbers here. You can arrange them using the first number, and then the remaining number is the leaf. If all the numbers are 222 or 333, the first two numbers will be the stem, while the last one will be the appendages. Okay, so for example, this number here is number 21. This number here is 26. This number here is 16, because I'm linking it up, with the initial stem. And this number here is 41. And you can see that we only have one of it here. Okay, so how do you do that? You arrange the data in order, that is from the least to the highest, and you separate data according to the first digit, and you make a display using the leading digit as the stem and the trailing digit as the leaf. So this is another example here. We have the stem and then the leaf. And from here, if I just pick like this particular number, that's number 36, because I'm linking it up with this number. This one is number 58, and this one is number 16, just like that. So look at here, some of the numbers were less than 2, so it started with 0. That means this is number 6, number 7, number 8. This is number 10, and this one is number 14. And one good thing with this kind of arrangement is, like, look at this one here. I can even say from here that number 17 is the commonest number because it's appearing 3 times. It has arranged it in a way that I can easily see the commonest number, in the presentation. And we have 2 number 50 just by, taking the 2 one after the other. Very simple. It's a very simple and straightforward way to organize your data. So this is a quick example that I think we'll just quickly do. There's a long jump and it is in meters. Okay, so we have our stem, and then we have our leaf. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 numbers. So we have 2.0 as the first one, or let me just say 2 points, and then 3 points, 4 points, then 5 points. So for the 2, we have 0.3, there is 3, there is 5, there is 5, there is 7, there is 8. That is what I've just done here. We have 3, 5, 5, 7, 8. For the 3, we have 2, we have 6, we have 6. For the 4, we have 5, and for the 5, we have 0. Done and dusted. As simple as that. Even from the stem and leaf, it's obvious that those in the range of 2 point something are more. We have about 5 of them, and only one person went that far as 5.0. So that's just a stem and leaf. It's not something that takes much time, but it's for you to know how it is done and how to interpret it. Dot plot is another type of display that can be used to organize our data. And interestingly, they are used for univariate data when the variable is categorical or quantitative. So it can be used for both types of data, either quantitative or categorical. So the dot plots can take the form of a bar graph in the design or a histogram in the design. Remember, the bar graph has spaces in between. Histogram does not have spaces in between. And there are 2 types of dot plots in case you are coming across them or you want to use them. We have the Cleveland dot plot and we have the Wilkinson dot plot. The Cleveland is the one that looks like the bar graph. The Wilkinson looks like the histogram. See the next slide. So this is the Cleveland. You can see that the dots are arranged like stacked on each other with spaces in between them. And looking at this particular one, it says the books that you read last summer. It's obvious that those who read one book are more. There are 6 of them. You get the point? Just by looking at it, if you look at it, it looks as if it's a bar chart. That's why we call it, it can work both like for a quantitative variable and a categorical variable. On the other side, we have the Wilkinson. It's also a dot plot, but you can see that it's just one dot, scattered within the chart. This is the Wilkinson, and it says men's long job records. It's obvious that the longest is 9.0 and is from US, while the shortest is Indonesia, about 7.9 or 7.8, and it's from Indonesia. So that is just an example. This is another picture of the Wilkinson. This one is for the Cleveland. You can see that it looks more like a bar chart. And this one is the Wilkinson, that looked more like histogram because of the simulation with frequency polygon. A line chart is also a kind of chart that you use to organize your data. It's just variables connected with a line. Variables connected with a line, that's one here, and you can have two variables, superimposed to just compare their appearance. A line chart can also have more than two variables. This one here has four variables, that you can use to just check different presentation. Then we have a time series plot. It's a type of line chart, but it's a continuous variable. It's basically continuous, and it's normally used for time. That is chronology. So a time series point has to do with dates, our time going forward. And that's just an example of a time series plot. Some of us do Forex, some of us do Forex. I've seen the picture before. That Forex, is it candle and whatever people call it? That's a sample of a time series plot. It goes up, comes down, goes up, comes down, depicting the different level of exchange, globally for you to reach to make your decision. Great. So for descriptive statistics, we say you can organize your data or you can summarize your data. This is what we have discussed. We have talked about the tables and we have talked about the graphs. Let's quickly look at data summary for descriptive data, that is to central measures of central tendency and measures of variation. And this one, like I said, is going to be calculation. So it can only be computed for interval or ratio data. That is quantitative. Interval or ratio data, what you can measure, what you can count. We have mean, median, mode, that we all know. I'm just going to be highlighting the particular areas that might be of interest to you above what you have been taught before. And then we look at range, interquartile range, variance, and standard deviation. So let's go on. The mean is the average. I don't need to waste much time here. You add all the numbers together, you divide by the total number of observations, and then you have your average, and that is that. So here we have a class of 13 students. What is the mean of their weight? You add all the weight of the 13 students, and you divide by 13. That is what we have here, and that is the mean. Likewise, in class B, you add all the weight of the 13 students and you divide by their number, and you have a mean. So what am I trying to bring out from this particular slide? Let me remove my... So if you just see this kind of data, and you are asked that which of the class is heavier, it will be difficult just looking at their figures. You can't do that often, but it is until you have an average to now realize that they are basically like the same weight, but you have some like a higher value here and there, lower values here and there. So they are basically like the same weight. They have the same mean value. So that is mean for you, okay? And what is the importance of mean? It is needed for inferential statistics, which we are going to start from next week, and it is not resistant to outliers. That's one concept I want you to know. Why am I bringing this concept? You might have your data, and then there's an outlier. You should not use a mean to describe your data because it will be misleading. An outlier is a person or a thing that is situated far away, is detached far away from the main body or system. A person or thing different from all other members of a particular group or set. That's an outlier. And I have an example as we continue. So look at this particular chart down here. This is supposedly a distribution for all of us, maybe in this particular class, and looking at our income, and then we have Dangote come to join us. The moment Dangote joins us in our group, Dangote becomes an outlier because if, let's assume we are maybe 120 in this presentation, for example, and then we have collected all our income, different income to form a data, and then we collected the income of Dangote, and we join, and then we divide it, the income, by 121, Dangote inclusive. By the time we have a value of our income, is going to be misleading, because the income of Dangote can equate that of maybe like 2 million of us, you know. So when you now find a mean with an outlier, it is misleading. That is why when you look at your data and you have an outlier, the mean is not the best to summarize your data. Outliers can make the mean a bad measure of central tendency, you know, or common example. So you can see if the mean is here, see where Dangote is, it's not a good measure. Look at it here, you know, see the number of people here, and then look at the number, just 3 people here, because they have a higher level of income, you know, it has like balanced the number on the other side. So the mean is not the best measure of central tendency when you have an outlier. Rather, you use a median, and we'll talk about that as we continue. So if Bill Gates walks into a village meeting, possibly maybe somewhere in Port Harcourt, there's a village meeting and he was invited, and we want to calculate the mean income of all the people in that meeting, it's meaningless, you know, because Bill Gates is a very serious, is a very rich person. Maybe we might end up having maybe $2 million, you know, for each person, and we know that that is not real, that is not realistic. That is why you must not use mean if you have an outlier in your, what's it called, in your data set. You use a median. So the mean is the best known measure of central tendency. It uses all the data because all the data must be added to get the value. And it is affected by outliers, either positive or negative. That's why you must not use it. It is best for normally distributed data. So when you do a histogram and your data is normally distributed, the mean is good for your data summary. Not usually equal to one of the original values, because an average, it has good statistical properties, and normally the mean is presented alongside the standard deviation, and we'll talk about that as we continue. The median value is when the values are ranked in order. The middle value is the median value, where you have an equal half up and equal half down. So when data are listed in order, the median is the point at which you have 50% of the cases above and 50 below. Another name for the median is the 50% percentile. So don't mix that, 50% percentile. So we have a class of 13 students and 13, so we can count, you know, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Number 7 here is the median, because it's just the middle number. We have 50% above, 50% below. No, not 50%. We have equal number above, equal number below. When we get to the 50% above, I will explain that. So the median of this data set is just 109. As simple as that. We all are familiar with median. Now let's assume one of the students drops out. That gives us 12 students. So let's assume this student with 59 drops out. We now have 12. And that brings up a little challenge, but no problem. We have 12 of them. So the two middle number will be added together and divided by 2. That gives us the median. That's just a little what's it called, modification when you have even number. But if it is odd numbers, you can just pick the one that is in between. But if it is even number, the two numbers in the middle is added and then divided by 2, and you have your median as 109.5. The median is not affected by outliers. So let's assume that maybe this one is, instead of 93, it is 93,000. Okay, no, that one will not work. It is a 1 here. Maybe 140 is 140,000. That's the one that will work because we are arranging them in order. So even if it is 140,000, it is still the last number. It's not affecting the median. So remember, if it were a median you were using for a situation where there's an outlier, so outlier does not affect the median, and the median will be a better measure of central tendency in case you have an outlier. Like I said, the median is unaffected by outliers, making it a better measure of central tendency, describing the typical person than the mean where data are skewed. So you can see the median is somewhere here. It doesn't affect. If it was the mean comes somewhere here, giving us a wrong impression. If the recorded values for a variable form a symmetric distribution, the median and the mean, they fall on the same side if it is symmetrical. You know, but if the data is skewed, the mean lies closer to the skew because the skew or the outlier brings it closer but the median is further away from the skew compared to the mean. That picture again, you can see where the mean is, and it's been affected by virtue of the weight financially of these three people. But the median is far away from the mean. You can see the median remains because it's just the middle. It doesn't have any effect with the outlier. That's the median. So the median does not use all the data available, and it is insensitive to outliers. It's a good descriptive measure, but it has poor statistical properties, and it is a measure of choice when you have skewed data. Let me repeat that again. It is a measure of choice when you have skewed data. The mode is the most common point in a data set, the one that comes up more. These are 26 students, and we are looking at the mode. 109 appears 3 times, and no other variable appears, no other value appears that much. So 109 is the mode, as simple as that. You might have a distribution where there's no mode. You can see this one, they are all U111, but here we have number 3 appearing 3 times. So here 3 is the mode. And you can even come to a situation where you have in a data set, maybe bimodal distribution, where 2 or 3 numbers are the most common in the data set. The mode gives you the most likely experience rather than the typical or central experience. Typical is median, central experience is mean, but the mode gives you the most likely experience. And in symmetrical distribution, when you have a normal distribution, the mean, median, and mode all fall on the same line. But in the skewed data, the mean and median, they lie further towards the area of the skew, and the mode remains the same. Look at that same picture again. The mode changes not. It's not affected by, what's it called, by the outlier, So you can see the median and the mean, they lie closer to the area of the skew where you have the outliers. So in a normal distribution, the mean is the same as the median, is the same as the mode. This is an example of a normal distribution, and this value here, where the red line is, that is the value of where the mean, median, and mode are equal. So in descriptive statistics, we've discussed the central tendency, talking about summarizing data, mean, median, and mode. Let's quickly look at variation, or the differences between groups. So the first one is range. You will have been hearing the range in a data set. We have 13 students in class A. The range is just the difference between the highest score with the lowest score, 140 minus 89, that is 51. In class B, 162 minus 80, the range is 82. Despite the fact, if you remember that they had similar mean, you can see that the range differs, and this has a meaning, and I will explain as we continue. So that's the range. Just to subtract the lowest value from the highest value, that's the range. Interquartile range is another type of measure of variation. It is a value that marks one of the divisions and breaks the series of value into 4 equal parts. So you have a data set, and it can be divided into 4 equal parts. The median is a quartile and divides the cases in half, or 50 percentile. That's just 50-50 on both sides. The 25th percentile is a quartile that divides the first fourth of cases from the latter for 3 quarters. So this is 25 percentile. This is the median. This is the 75 percentile. So here we have 3 quarters. Here is the last 1 quarter. Here we have 1 quarter. Here we have 3 quarter. For the 50 percentile, there's 50 here, there's 50 here. That's just the interquartile range. Let's look at this example. There are 12 patients, and they were examined to see the number of push-ups they can do after a plate of food. And this is the number of push-ups they can do after the plate of food. There's a question here that says, find the 3 quartiles. That is the Q1, Q2, Q2, and Q3. This is the 75 percentile, 50 percentile, and this one is the 25 percentile. Find the 3 quartiles and the semi-interquartile range. Interquartile range is Q3, the value of Q3 minus Q1. So let's see if we can quickly do this one right here now on the screen. There are 12 of them, and we are supposed to arrange them in ascending order for you to find the median anyway. So we have number 8, another number 8. Okay, let me be removing them. And then there's number 9, And then there's number 10, 11, I think I can see 12 there, 14, 1, 2, 3, 4, 1, 2, 3, 4. As you can see, 14 is the mode because it appears 4 times. Then we have 16, then we have 19, 16, 19. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's the number. So if you are to do this, I will advise you to start with the Q2, that is the median, 50 percentile. And there are 12 numbers. So 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So these are the two numbers that form the middle. And 12 plus 14, that is 26. And 26 divided by 2, that is, what's it called? That is 13. So our Q2 is 13. And that divides our distribution into 2. And our Q1, which is the 25 percentile, is also the median of this side. And our Q3 is just the median of this side. So our Q1 is for us to now add 9 plus 10 and divide by 2. That is 9 equals to 9.5. And then our Q3 will just be 14 plus 14 divided by 2. That is 14. So our interquartile range is now 14 minus 9.5. I think that should be 4.5 if I'm not mistaken. That should be 4.5. But the question says we should find our semi-interquartile range. Semi-interquartile range means that we should find the half of that value. That's 2.25. And that's the answer to the question. So it's very straightforward. You arrange your numbers in ascending order. You find the median, that is Q2. And then you find the median of the remaining two sides, Q1 and Q3. And from there, you can find your quartile range or semi-interquartile range, okay? This is another example. We have a box plot here. We'll talk about a box plot, and it shows us the value, of the 25 percentile and 75 percentile. Our Q1 here is 4. Our Q3 here is 15. And our Q2 here is maybe 10.2 or 10.5, thereabout. Well, it says what is the interquartile range? It's just Q3 minus Q1, that's 15 minus 4. This is 11. Very straightforward. It doesn't require any big deal. If the data set is very massive, there's a way you can use the formula, but that is not for this class for now. Variance is a measure of spread of the values. Remember when we were talking about the histogram and the frequency polygon, this is an example of a platycotic distribution. If you remember, I was telling you that it's flatter, okay? And this one is a leptocotic. By the way the presentation is looking like leptocotic. So variance is just to check the spread of values of a variable. Consider these numbers, 55555, 13894, down to the last one. If you find the mean of these numbers, all of them are 5. That's the mean. But this one, if you look at it, is a constant. You now remember why we are talking about types of variables. This one is a constant. And these ones are variables because they vary. Now, if we are to look for variation, there is no variation here because everything is the same. But there can be variation here because they vary one from the other. So it spreads out. That is what we are talking about, variance. Look at this example again. We have this class A and we have the weight of 13 students. Remember that we calculated the mean earlier on to be 110.5. So the question is, what is the deviation of this weight of each of the students from the mean? We want to know how far are they away from the mean. Yeah, that's the right word, the variance. How far are they away from the mean? That's the deviation. Okay, so we will check the deviation of each of the weight from the mean. So the deviation of the first student will be 102, minus the mean. For this particular student, it will be 105 minus the mean. And we have figures. But look at here. You'll notice that the deviation is negative because the person's weight is less than that of the mean. Where here it is positive, the person's weight is more than that of the mean. So if we do it for all the students, we would get 0. Why? Because the negative value, we eliminate the positive value. That is what we call, that is what will happen. So to be able to work out what we are looking for, we will need to square all those values. So the value of each student minus the mean, you square it, that will make it to have a positive value. And then we can now add it to find out our variance. So going back to that first patient for first students, where we have a negative value, if we square it, we have 72.93. And that one too that has a positive value, if we square it, we have 19.89. We can now do that for all of the students and add all of the values together. Those values added together is what is called sum of squares. And you'll be hearing that terminology if you are doing biostatistics, sum of squares. That is the initial value minus this mean, and then everything added together. This is sigma, it's add up every value. So we have something like this. Please look at this. So these are the initial scores, but we can now subtract them each from the mean and square everything. You can see that everything is squared here. And our sum of square is here, 2,285.39. That's our sum of squares. So in variance, the last step is now to find the average, of the sum of squares. So if you are working with a population, that means your study has taken cognizance that everybody in that population is involved in your study, you use N. But most of the time, we use a sample, and that is where you have to factor, that variation into your sample, N minus 1. So like we did in the previous slide, where you have, is it 2825, because what we are working about on is the sample, we use n minus 1. There are 13 students, so that will just be 12. We'll divide it out, and that will give us the value of our variance. That's just the formula, what I've just explained it here. Okay, so we have that, and we have 235.45. But the question is, what does that mean? What does that mean? So variance of 35.45, how is that useful? It means very hard to interpret. And remember that the value here is squared because our variance is sum of squared, okay? So because of the challenge in interpreting variance, that is why the standard deviation was brought into being. And the standard deviation is just the square root of the variance that we have calculated. The standard deviation is just the square root of the variance that we have calculated. So variance is S squared. Standard deviation is the square root of S, which gives us S. And that is the formula. You don't need to memorize that, except you want to just have that at the back of your mind. So if we now find the square root of that 235.45, we have 15.34. Now, this one has a meaning. What does it mean? It means that the average person's deviation from the mean weight, is 15.34. So that's the average deviation of each of the students from the mean weight. Each of the students from the mean weight. As we continue, I will explain what that means. Look at here. Larger standard deviation means there's greater amount of variation. When your standard deviation is big, it means that the range is also large. That means the people are not like clustered together. They are scattered. As we continue, there are other examples to make it clearer. So here we have a standard deviation that is 6. Here we have a standard deviation that is 3. And look at the distribution. This one looks like a normal distribution. This one looks flat. But they all have the same mean. So it gives you an idea of the kind of distribution. This one is flat. It's because, the values are spread. If standard deviation is 0, that means that you have a constant. If standard deviation is 0, it means you have a constant. If you are to rescale your standard deviation and you change the unit, it doesn't affect anything. It will change by virtue of the unit the way it is. And like the mean, the standard deviation will be inflated by an outlier case also. And I will give you an example. Let's assume we have an outlier. Our mean, is 25. It's possible you can have a standard deviation of maybe 40. If you see something like this, it obviously shows that you have an outlier in your data set, and you shouldn't have used a mean to summarize your data set, because the moment your standard deviation is greater than your mean, then there's an error somewhere. Instead of using mean, you should have used a median. Those are some small tidbits. So look at these numbers again. Like I said, their mean for the four of them is 5. We cannot calculate the standard deviations for each one of them, but I can tell you that this one will have the highest standard deviation because it has the highest variance. The numbers are far from each other. Let me even give you an example. Let's find the range. We have said range is highest minus lowest. Range here is 0. Range here is 9 minus 1, which is 8. Range here is 9 minus 4, which is 5. Range here is 6 minus 4, which is 2. So for even the range, I expect that my standard deviation will be highest from there because it is widely, different. They vary one from each other. Okay, so this is a normal distribution, and this is where we have the practicability of what we are talking about. In a normal distribution, please listen carefully. 68% of your distribution lies within the mean plus or minus 1 standard deviation. I will explain what that means in the next slides. You will understand more. 95% of your observations lie that's in a normal distribution, lie in the range of the mean plus or minus 2 standard deviation. 99% lies in your observation between 3 plus or minus 3 standard deviation. What does that mean? What does it mean? Let's continue. So if a distribution of data is approximately symmetrical or bell-shaped, about 95% of the data will fall within 2 standard deviations of the mean. So you can have the negative part here, you have the positive part here. When I give an example, you understand what I'm talking about. And then, like I said, the 68% is 1 standard deviation, the 99% is 3 standard deviation. Look at this class example to explain what I'm talking about. Suppose the reaction time of a particular drug, that is analgesics, has a normal distribution. And then we have a mean of 10 minutes and a standard deviation of 2 minutes. Okay, so like I said, our mean is normally reported with a standard deviation, okay, plus or minus 2 minutes. What does this mean? What does this mean? I go through it again. The reaction time of a particular drug has a normal distribution, okay, with a mean of 10 minutes and a standard deviation of 2 minutes. What does this mean? Go back to that, our chart. We said that 68%, would be plus or minus 1 standard deviation. Remember, our mean is 10 minutes plus or minus 2 standard deviation. So for 68% of the people in our study who had a reaction, plus this one is for the 68%, 1 standard deviation, that is 8. That's 10 minus 2 to 12 minutes. That means 68% of our population who had a reaction, between 8 to 12 minutes. Remember, our mean is 10. Now, if we are looking at 95% of the population, they will have their own value between the mean plus or minus 2 standard deviation. And our standard deviation here will be 4. That means that 95% of the population will have reaction minutes between 6 and 14 minutes. And 99% of the population, their own reaction is 3 standard deviation. 3 times 2 will be 6. That will be between 4 and 16 minutes. That's how you interpret, for practicability. That's all I'm trying to say. So for the 68% of the subject taking a drug, they will have a reaction between 6 and 12, between 8 and 12 minutes. Remember, our mean is 10 plus or minus 2. This is 1 standard deviation. 2 standard deviation is 4. 3 standard deviation is 6. It's just 3 times 2, 2 times 2. 95%, because this one is 2 standard deviation, 99% is 3 standard deviation. 95% we have reaction between 6 and 40 minutes, because that one will be 4. This will be 4 for 95%. So 10 minus 4, 10 plus 4. That's how we got here. This one is 10 minus 2, 10 plus 2. And for the standard deviation for 99% is going to be 10 minus 6, 10 plus 6. And that's how we got 4 and 16 minutes. That's how you interpret standard deviation for different proportion. Look at this example here. We have a test in class A. We have the same test, another test rather, in class B. And the total is 640, 640. And they had the same number of students, but when the mean was found, the mean was 80 in class A, the mean was 80 in class B. But the standard deviation in class A is 5, the standard deviation in class B is 15.8. So that is where you need to now apply the knowledge of standard deviation to interpret your findings. Excuse me. This means that the values are closer together because the standard deviation is smaller. And you can see from here, we have 72 and then we have 87. We can even find the, what's it called, the range. The range here is going to be 15. I think the range here is 15 because it is the biggest number minus the smallest number. But here you can see that the smallest number here is 60, the biggest number is 100. And the range here is 40. Is it not making sense? That is why the standard deviation is higher. So when you see figures, nobody will give you the raw data. When you see figure 80 plus or minus 50.8, 80 plus or minus 5, you can, from that, extrapolate how the data looks like. That definitely in the data, there will be a high range. Some values are lower than the others, some values are higher. But when the standard deviation is very close, it just shows that all the values are not far from each other. And like I said, when your standard deviation is greater than your mean, you have an outlier, and that mean is not the best method to summarize your data. Okay, so we have looked at range, interquartile range, we have looked at variance, we have looked at standard deviation. Let's look at the box plot. And the box plot is a very beautiful graphical method in descriptive statistics to show a lot of values of your variables all at once. The box plot will show your upper quartile and lower quartile. Remember, upper quartile is Q3, lower quartile is Q1. It will show it at once. The box plot will show your mean, it will show your median, it will show your range, and it will let you know if you have an outlier. The box plot will let you know if you have an outlier in your data set. Okay, that is how a box plot looks. It's also called a whisker plot. You can use it to denote different kinds of variables, and it's a beautiful chart. If it is if you do it, it's a beautiful chart that you can use. By the way, before we even go there, you can see 1, 2, 3, 4, 5, 6, 7. If you look at 2, 4, and 7, there's a dot outside. And if you look at number 5, there's a big a darkened dot here. Those dots, this one, and this one, are outliers. This one here, the one on Friday, that is darker, is far outlier, very far. You understand? And they all have implications when you are reporting your data set. This is another example of a box plot, for different kinds of trucks and mileage, different colors for different kinds of vehicles. This is another example of a box plot. They come in different design, but this is the interpretation. When you see a box plot, they normally have these different markings. Like I told us earlier on, that circle outside denotes an outlier, and the top part of the box plot is the maximum value, while the lower part here is the minimum value. That line inside is the median. The top of the box is the Q3, the lower part of the box is the Q1. That's the lower quarter. This one is the upper quarter. This median is the 50th percentile. Please let me go back to correct something. It's I don't think the box plot shows the mean. It's the median that it shows. That must have been a mistake there. It's the median that it shows. It doesn't show the mean. The mean is calculated from your normal calculation. So like I said, you have an outlier, you have the maximum value, you have the minimum value, you have the upper quartile, the median, and then the lower quartile. That is what you see in a box plot. So Box plots have those lower quartile to upper quartile with a median marked. They portray a 5-number summary of the data. You have the minimum, you have the maximum, you have the median, you have the lower quartile, you have the upper quartile. Okay, so for this particular box plot that we see here, I can say the minimum here is around 59. I'm talking about the Q1 here. I can say it's around 59, and the maximum I can say is around 98 or thereabouts. I'm talking about this one here. This is an outlier, like we've explained, and I can say my median should be like maybe 76 or so. This is what I'm talking about. That's my median. So that line in between that box. And my Q1 is 70. That is and my Q3, I can say that was like maybe 84 or thereabouts. So you can pick out those variables from a box plot. There is a formula for calculating an outlier in a box plot, and that is because outliers can be either above or below. So if an outlier is below the lower quartile, it is the lower quartile minus 1.5 interquartile range, and interquartile range is Q3 minus Q1. So if we know the value of the interquartile range and you multiply it by 1.5 and subtract it from the lower quartile, then you can have the value of the outlier if it is below. If it is above, it is still the upper quartile plus 1.5 interquartile range, and then you get the value. So, for example, if our lower quartile is 2, our upper quartile is 8, then our interquartile range will be 10 minus 2, which is 8. Our outliers above will be 10 plus 1.5 times 8, and that will give you 22. So any figure 22 and above is going to be an outlier. Any figure 22 and above is going to be an outlier. Now we have some little insights to use descriptive statistics, but there's something I want to show us beautiful. So this is just an example of a data set, and it is giving the summary of a variable age, and age is a continuous quantitative variable because age can be measured. It's a continuous quantitative variable. This is an example of the histogram. So it's not every time that your histogram has been normally distributed or what have you, but that's just an example of what it brought out. But this is what I just want to talk about because this is what we have been discussing. Okay, so for the age, we have the mean given as 90.41. We have the standard error, which I'm not going to talk about now. When we get to t-test, we can start talking about that. We have the median and the mode as 84 and 84. We have our standard deviation as 30, and that should let you know that there is a wide range, between the age. So apparently, it's not a correct variable. It's just like, for example, because you cannot have an age at 90 and then you're having a standard deviation with 30. That is telling us that some people are 120 years old. So let's assume let me just say it is weight. Don't let us use age because age can bring confusion. So let us weight because it's just hypothetical. So we have the standard deviation being 30 and we have the variance being 913. So from this table, all I'm trying to bring out is you should be able to explain what you are seeing on this table. If you come across something like this, from a statistical output, maybe you have given a statistician your work to do, and then you are given a table like this, you should be able to explain what you are seeing there. The standard deviation is 30, the variance is 913, and how did we get the standard deviation? Just the square root of 913.8, and that gives you the 30. The kurtosis and the skewness, okay, let me just explain something about the kurtosis and skewness, because I didn't go far. Remember I told you kurtosis is a measure of how clustered around the data are to the center. So ideally, kurtosis should be 0, skewness should be 0. We spoke about skewness. This is a long right skewness. This is a long left skewness. Kurtosis and skewness ideally should be 0 because it has its formula for calculating them. 0 means that there's a normal distribution. If you have kurtosis and it is negative, that means that the distribution is, by virtue of histogram or the frequency polygon, is a bit flat. The skewness between -2 to +2 is actually taken as normal. So we can say this particular presentation is okay, it's not too skewed. And even the kurtosis, it's just -1. It's not so bad. But there are situations where you have it very high. That is where we know that there's a problem. The range, we understand what the range is. The range is the smallest number minus the highest number minus the smallest number. And this is the smallest number, this is the highest number. That is how we got the range. The sum is to add up all the variables together, and the count here shows that there are 60 observations, which make up the data set. I think I would like to stop here to give some time for questions, comments, contributions, and how we can continue. I'm hoping in the course of these classes, we'll be able to squeeze out some time to do some analysis on SPSS with some sample raw data to just like grant some practical perspective to all this English that we have been saying since morning. Over to you, Dr. Sam.
Oh, thank you so much for this very brilliant presentation on Introduction to Descriptive Statistics. So there are lots of emojis, people clapping, and I'm appreciating you for this very important talk we have had. So we'll just take within the next few minutes some questions, but before then, just a quick recap. We've had a session on Introduction to Descriptive Statistics, talking about what variables are, the different types of variables. We looked at scales of measurements and how we can use scales of measurements and for which types of data. We looked at data, variables, information, and then we also looked at how to present data. We looked at organizing data and summarizing. We looked at measures of central tendency. We've looked at a whole lot within the past 1 hour, 30 minutes. So at this point, we just want to take a few questions. Before we take the questions, there's a hand raised up. I want to acknowledge Professor Morenike Upong, who is here with us. Could you please go ahead, ma, while we... Ma, Professor Morenike, you may go ahead with your question. I think her hands are up.
Yes, I don't know if you can hear me now. Yes, I'll stay or muted me. Yes, thank you very much. I just want to thank you again. 2 things I want to say for everybody here. We don't have a small fish in the house. We have the CEO of ICOH, and he's coming here for 4 weeks. I do not take this for granted. This is a big, big fish who's been here. Thank you, sir, for always being here. I was at another meeting. When they didn't have questions, I just said, look, let us round up. I left because I don't want to miss this. And of course, it's a pleasure to be here and learning again. Thank you so much, sir. And that's all I wanted to say. I just truly, from the depth of my heart, want to say thank you. Over to you, sir.
Thank you very much, Ma. And we are really so grateful for having you here with us. And thank you to our very esteemed lecturer for today. And I must say, it has been a very engaging session. We've had the Zoom on full capacity, and it has remained so. And we've also had lots of viewers on YouTube. At a point, it was over 80, almost reaching 100. So that's just to show how important this session has been. I'll just take, I see a few questions on the chat box. There is a question here about line charts and frequency polygon. So there's a question, are they the same?
Okay, beautiful. So maybe I should still share my screen and see if I can take you back there. So the line chart, if you notice, it doesn't have to start from what's it called? The lower end. The frequency polygon is more like a dome-shaped, bell-shaped structure. So a line chart, where is my slide? Can you see my slide? It's not moving.
We can see it. It's on the last page.
Yeah, I'm trying to. Okay, maybe I should just exit it. Let me stop sharing and see if I can come up again and show you. But what I'm trying to say is that a line chart does not have to start from the lower end on the left side like a frequency polygon. A frequency polygon has that simulation of being like a bell-shaped design, starting from one end and going to the other end, to, I think I'm okay, yeah, I should be able to pick it now. Great. Let me just scroll down. Okay. I think it's beautiful. All right, so if you notice a line chart here, it's starting from like maybe this 50, and then I will just go back and show you a frequency polygon. The difference is that the frequency polygon starts from under and goes up and comes down. I don't know if that's making sense. I can't even find where my frequency polygon is again. Excuse me. Great. So look at the frequency polygon. It comes from down, it goes up and comes down. Look at this one also. Comes from down, goes up and comes down. But for a line chart, the value, look at this example of a frequency polygon. So the frequency polygon simulates a normal distribution. So it must have that normal distribution appeal, either with some skewness or some kurtosis. But a line chart does not have to start from down and go up. A line chart can start from any aspect and then continues like that. I'm trying to bring up the line chart again, just for you to see if you can appreciate the differences, in the two. So this is a line chart. You can see that, for example, the one on 50 here is not starting from down and going up. It can start from anywhere. They look alike, from afar, but that's just a salient difference between the two of them. I don't know if that makes a bit of sense.
Thank you very much, sir.
Yeah.
So there's another question here. It says, what you are saying is that we should not remove outliers from our data when cleaning, but we should use appropriate statistical tools when reporting.
Exactly,
that's right.
perfectly.
Yes.
Because it's part of the data. Once you remove an outlier, then your data is distorted, and then you're giving us, you are misleading us invariably. Because an outlier is part of the data. So you just use the appropriate tool to present or to present your data. Don't remove an outlier. You'll get the point. I so much love that comment. But I remember the last class I had, Professor Morenica emphasized this particular sentence that the person said, and I'm excited that it's coming up again. Please don't remove an outlier. Just use the appropriate text to present your data. Beautiful, beautiful. Thank you so much.
All right, thank you, sir. There's another question on, so people are asking, yes, you will get the slides. Somebody is asking about the importance of the standard error. Okay, so what's the importance of the standard error?
Yeah, so I remember I mentioned it that I don't want to bring it up here now because of the relevance. It's more relevant when we start talking about t-test. One thing I have learned over time in talking about quantitative data analysis is like it's a building block, and it's a step at a time. There are actually many things I didn't mention in the course of this presentation, as in many things, because if I bring them in, it might not be the best time to introduce them, and I don't want to scatter what I'm like building up. So I can assure you that by, our next class, to be the third class, when we're talking about t-test and ANOVA, I will bring in the concept of the standard error, and if I forget, remind me. It will be best suited at that level, so that I don't bring in concept that will scatter the little that we have been building since morning.
Thank you very much, sir. That's well appreciated. Okay, so I think there are some questions about outliers. People just need to understand really what outliers are and why we have to switch to median when we have an outlier. So maybe if you could just give, I know you explained it during the course of the lecture, but maybe if you can just talk about it a little again so there can be a better understanding.
I think it's nice. That's why we are here. It's an opportunity to re-explain it. You know, I was in, what was it called? Many years ago, I had an opportunity to be in China. And for those who had seen me, Professor Morenike knows me. I'm tall. I'm more than 6 feet. I'm about 6'4". And then I went to a dental school, and most of my hosts then, the students, you know, they were seeing somebody so tall. And all of them came, you know, to snap pictures with me, possibly for their records. And when I was going, I was thinking to myself that if I was in a room with like 4 or 5 of them, and then we were to calculate the average height of the people there, and that height is now like presented outside, it will be misleading. Because let's assume, 1 minute, let's assume I was this tall. Most of them were like here at my level, just a bit above my waist. You get the point. And if we are going to calculate the average height of myself and like the 4 students that were taking me around, we might be having something like that as our average height, but that is obviously against and it's like misleading because they were not that tall, even for an average height. What is there is because my own height had like added extreme values that were not existent, you know, into that picture to make them look as if they were. There's a statement I want to show us here. Okay, if Bill Gates walks into a village meeting, our mean income becomes meaningless because we all become millionaires, if not even billionaires. Because by the time you calculate the wealth of Bill Gates and add it to our own wealth, and you find the average, you will see that it will be misleading. So an outlier is a value that you have gotten. You might have such values, except it's a mistake because sometimes you want to type 11 and you find yourself that you have pressed your keyboard 3 times and you have 111. In that situation, you need to cross-check with your questionnaire, whatever source, to see if it was a mistake on your part. Because this can be an outlier if it was a mistake, and in that situation, you need to correct it. You know, but if in actual sense, somebody, you know, was 100, while the next person to them and below were 60 and like below, and you are sure that your 100 is 100, not a mistake, then it has to stand. However, when you are working with outlier and you want to summarize your data, you don't use a mean because the outlier will pull your mean away from the reality and it will mislead. Rather, you use other measures of central tendency like median or mode. You know, so cleaning data has to do with if it was an error on your part, error of imputation, you know, but if it was an actual value, you need to have it there because people need to know that in that particular data set, there was this extraneous value that you have. So outlier is not always a mistake, but it's a finding that is worth mentioning, you know, for comparison purpose. Somebody might come across another outlier somewhere, and then it can give an idea of a pattern. So I was just emphasizing over and over that mean is not good in presenting or summarizing a data that has outliers. That is one aspect I'm trying to emphasize so that, you know, going forward, at least it shows that you have an insight on how best to present your data. Rather, you use a median because the median does not, it doesn't use all the values, it's just the middle value, you know, and it also expresses a summary of the data set, the central value of the data set, or you can also use a mode. And that's all I'm saying. So outliers can be from an error, or it can be a real finding. But if it's a real finding, please don't use it, don't use a mean to explain your data set, rather use a median. So I think that's just basically what I'm trying to emphasize concerning outliers. Let me give an example of where you can have outlier. I did some studies in the past with a viral load, that's HIV and AIDS, and you'll be surprised that, you know, you can have somebody who has a viral load of 0, and you can have another person that has viral load of maybe millions of copies. So the data set is usually filled with outliers. And in that situation, we are not permitted or it's not advisable to be using a mean, because even people that don't have any viral load, you will be giving them an impression as if they have viral load, but rather we use a median. And you need to also explain, if you want to add like a footnote that you've noticed outliers in your finding, in your data set, blah, blah, blah. But the point is that outliers in a data set is better to use a median or a mode in summarizing the data. Over to you, Dr. Zhang.
Thank you very much, sir. So I think that that's clear, and it explains it so well. I'll just take one other question, this time from YouTube, but it's also a lecture. It's a question similar to this one we've had. Maybe it will just follow up as a natural, it's a natural follow-up to this question we've just answered. So the question is asking about, since we use median for outliers, can we then present it as median plus or minus standard deviation? So,
no. Okay, so if you recall, the mean, it's an average. You calculate everything, and then you have the standard deviation to know how far each value is far away from the mean. That is the standard deviation. So a median, let me just show you. There's something that's, okay. The median does not use all the value. That's where I'm looking for. The median is unaffected. Okay, no, not there. But all I'm trying to say is that it's just a number that you pick that just reflects, the spread of the data set. So you are not calculating a standard deviation for a median. It's not part of what you need to report for a median. A median is just a number that describes the typical part of the data set, just the middle part. If you look at it from top down or down top, just the middle part. So it doesn't require a standard deviation because the median is not the average. It is the average that requires the deviation, the standard deviation of each of the numbers of the values from the mean. So a median is just reported median, and you give a value. You don't need standard deviation added to that. Thank you.
Thank you, sir. I'm sure as we proceed during the course of the month and we take more sessions, it will get much more clearer to us when we even start talking about inferential statistics and the likes. I just also add that typically when we need to report median, sometimes you may see it's reported with interquartile range, and that's because there are outliers at the extreme ends. So like he has rightly said, you don't report your medians with standard deviation because of course, it's not appropriate to use your means. Your standard deviation typically goes with means, while if you're reporting median, you just report it, or you may want to include your interquartile range with the median. So thank you so much for that. I think we have time. We still have time for maybe one more question. So someone is asking, how does the bigness of standard deviation determine that there is an outlier? Is it in terms of its ratio to mean, or what? Is there any other way?
Yeah,
So
good
that's another
question. Good question. So let's assume that we have a data set of maybe like 40 variables, possibly talking about distance of a particular, maybe somebody like a short put, maybe we are throwing a short put and then we are measuring the distance and we are looking for the mean, and possibly it's in meters. So we have maybe a group A and then a group B, all of them 40 sportsmen throwing the shot put. So let's assume the first group A, we have maybe 13 meters plus or minus 4 or 5.4, meters as their own shot put distance. And then for the group B, we have, let's say 14 plus or minus, let's say 17 meters. As you can see from here, the 17 is already more than the 14. 14 is the mean. The moment you have a standard deviation that is greater than your mean, is an evidence of an outlier. So this would not have been the best way to report this finding. Rather, you will have just like arranged your data or use the SPSS or data or Excel or EPInfo to get your mean value. So because of this finding, you will now opt for the median, and like Osaon added, with the interquartile range, just to give us an idea. And if I, as a scientist, am reading your work, by virtue of you reporting the median, I know that you must have observed that there's an outlier, that has distorted, the finding if you wanted to use a mean. I don't know if that's making sense. So the moment your standard deviation is more than your mean, it's an evidence of an outlier. The moment is more than your mean, it's an evidence of an outlier. And that is when you have to change and then report it using a median. Does that make sense?
Thank you very much, sir. Okay, so I just got this last question from YouTube, which we'll just take, and after this, we'll call it a day. So this is just a simple statement or question. When do you use box plots? Specifically, when do you use box plots?
It's just a way of summarizing your data. It's dependent on you. The same data that we've been talking about, those students' weight, those 13 students in class A and class B, I could choose to present them as a box plot. It's just graphical, it looks tush, it looks scientific, it looks appealing. So it's not as if you have any particular situation when it should be used. But if what you want to communicate has to do with mean, median, maximum value, minimum value, and those interquartile values, then you use a box plot. It's not every time that you are interested in reporting the interquartile range or the percentile. So if you have the desire to report those variables, and more so to even compare it with another set, so you might have 2 or 3 sets. Let me show you what I'm talking about. You might have 2 or 3 sets of values that you want to show. Okay, beautiful. Like here, there are some values here. I wouldn't know what the purple, the red, and the green stands for. The purple might be maybe the speed, the red might be maybe the weight, the green might be, but it has to be a quantitative variable. And you are trying to compare for an SUV, a sedan, and for a sports utility vehicle, a truck, and a wagon. You can see now that it's just like summarizes so many details in one chart. You can use a box plot for that. Otherwise, if you're not interested in comparing with all these others, you can use it for one, or you can express this one by mean, median, mode, or standard deviation or variance or whatever. So it's a choice based on the kind of information you want to pass across, and how you want to pass it across. This looks, beautiful. It looks appealing, and also, like, if you are making maybe a kind of abstract presentation in a conference, there's a way you present some of your chart, that catches attention and people want to hear what you are saying. So it's a choice, and obviously you use it again when you can interpret it. There's no point putting up a chart and then you are asked what does it mean and you are saying actually, then that's a serious one. So once you are competent about what it means and you can describe and explain the parameters it's displaying, I think you should go on. So in a nutshell, it's a reflection of what you have in mind to explain or present to the audience or to those who are reading your work.
Once again, I want to really appreciate you and thank you so much for this very elaborate session we've had this morning. I must say I've heard lectures and sessions on statistics, but this is one with a difference. I want to really appreciate the fact that you have been able to break it down to the level in which everyone, whether it's a novice or is someone established, can really follow. And it's been a really engaging session. We've seen lots of participants both on YouTube and on Zoom, and everyone is appreciating you and thanking you. This is just to tell us that we have a lot in store. After today, we'll still have more sessions. We'll have it again next week, Saturday. We'll have it the upper Saturday and the last session and the last Saturday of this month. So please do well to ensure that you are here for the next session. And at this point, we would like to thank you all for participating, all of our various audience, both here and on the YouTube platform. Thank you so much and enjoy the rest of your day.
Thank you, Dr. Sao. Thank you, everybody.
Thank you very much, sir. Hello, Toby. I think we can end the session. Thank you very much.